Biopsychology. Basic questions we're going to be looking at in Lecture 2. What are the brain imaging methods that are used to study brain structure and function? What are the cerebral hemispheres? What are their functions? What are the lobes of the cerebral cortex and what are their functions? What are the key structures and functions of the hindbrain, midbrain, and forebrain? What is meant by the term brain plasticity? So we're going to be looking at the brain. Let's go back in time a little bit. Franz Gall developed a technique for discerning different personality traits and attributes known as phrenology. And this became very popular, and what it involved is mapping out lumps and indentations and so forth on the skull, and then the phrenologist would palpate or feel around on the skull and then be able to tell you something about your inner personality traits and attributes. Very popular, but absolutely no scientific basis for this whatsoever. The idea was that there was an association, some association between the shape of your skull, the lumps and bumps and so forth, and something about your personality. But there was absolutely no scientific evidence for that whatsoever. So it was very popular for a while, and then it was sort of written off by serious scientists as pseudoscience. Franz was somewhat headed in the right direction because now we know that there's different parts of the brain that are associated with various traits and attributes and behaviors and that sort of thing. So there is association between the different parts of the brain, but the shape of the skull has nothing to do with that. So many of the early studies and case studies and so forth that revealed the relation between brain and behavior were unfortunately found in people who had suffered severe trauma. Phineas Gage is sort of a classic example of this. Phineas Gage was described as possessed a well-balanced mind, was looked upon by those who knew him as a shrewd, smart businessman, very energetic and persistent. Gage was a foreman working on the railroad. He was in charge of people. And then, unfortunately, he had an accident that sent a railroad spike right up through his left lower cheek and out through the top of his skull. So here he is holding the actual spike that went through his head, basically. So thereafter, he survived. He was described as quite a different person than he was before the accident. So fitful, irreverent, indulging at times in the grossest profanity which was not previously his custom, manifesting but little deference for his fellows, impatient of restraint or advice when it conflicts with his desires, at times pertinaciously obstinate, yet capricious and vacillating. So Gage was a different person. So you change the brain, you change the person. So case studies like the one of Phineas Gage really helped reveal a lot of information about what was going on between different parts of the brain and personality types and motor behavior and that sort of thing. So there was this unfortunate upside to people having these injuries. These days, we don't have to wait for people to get injured. Actually, here's a slide that shows a rendering of maybe what had happened with Gage. So given the skull and so forth, evidence when he was alive and studying him and that sort of thing. This is an image that kind of shows you what happened. Went right up through his lower left cheek and right up through his frontal lobe. So fortunately, we don't have to depend on people that suffered trauma to their brain to learn something about brain and behavior. Now there's all kinds of different technologies that support this. So we're going to look at 4 of them: computerized tomography, or the CAT scan, positron emission tomography, or the PET scan, the MRI, which you're probably familiar with, and there's a functional MRI, which is a really very, very interesting technology that's being used rather extensively these days to learn about brain and behavior. So let's start with the CAT scan. So the CAT scan, the computerized tomography scan, uses X-rays, and it creates a nice 3-dimensional image of whatever it is that you're running through the CAT scan. So here you see a cross-section of somebody's head, and it gives you that nice, crisp 3-dimensional image so that you could observe any structural abnormalities. And then the PET scan of the positron emission tomography has typically a radioactive, it's a harmless radioactive substance being either injected into your blood, or people will ingest a fluid. It's kind of awful tasting. They try to make it so it's kind of tasty, like strawberry and orange, different flavors. But I've heard it's pretty awful tasting. So you have these radioactive isotopes ingested or injected, and then they make their way to the brain. And then in the scanner itself, it detects where those isotopes are being metabolized in the brain, and the different parts of the brain that are working more so than others are kind of lit up in different colors. So here in the red, you can see the different part. One part of the brain is working. There's more metabolic activity, more blood flow to that part of the brain than others. So you can map out in real time what's going on in different parts of the brain. So you put somebody in a PET scan and have them solve some sort of cognitive task or motor task or something like that. And the different parts of the brain that are more active when they're doing that task are lit up. And then there's the MRI, magnetic resonance imaging. The main difference is that between MRI and the CAT scan is that the MRI uses magnetic fields. X-rays aren't terribly healthy for us, so the MRI is an alternative. Uses magnetic fields and radio waves to generate the nice 3D image. And so here we're looking at, this is an example of MRI images. So these are cross sections of a brain of somebody in their 20s, somebody in their 80s aging gracefully, and then here's a person in their 80s with mild Alzheimer's. So you can really see the structural differences in a healthy brain against an older person's brain with mild Alzheimer's. So good at detecting structural abnormalities. And then lastly, we have the functional MRI, the fMRI. This is a great technology that is similar to the PET scan in that you can observe what's happening in the brain in real time. The fMRI monitors blood and oxygen flow to different parts of the brain. So the different parts of the brain that are working, using more oxygen, for example, in metabolism, are lit up with different colors. So you can see, again, in real time, what's happening in the brain when people are solving problems or doing motor tasks and that sort of thing while they are in the fMRI. So there's a lot of interesting studies looking at a lot of different things. Here's one that looked at sort of the power of the mind, so to speak. So researchers scanned the brains of 21 volunteer wine novices, measuring sensations in the part of the brain where flavor responses apparently register. So there's a part of the brain that's dedicated to registering flavor. All right, so the subjects were told only the price of the wines. They tasted one wine twice and were given two different prices for that wine. So they simply gave them the same wine, two groups of people, the same wine, but they just told them that the prices were different. So which wine do you think they liked better? Maybe you guessed it. Well, they preferred the one they thought was more expensive. So this is how people that brand and price and so forth, they know that if something is expensive and you think you paid a lot for it, then we're going to have a different response to that. Subjectively, psychologically, we're going to quite possibly think, oh yeah, this is a higher quality wine than the one that's cheaper. But interestingly, the different parts of the brain that are registering flavor, or the parts of the brain, register differently. So the brain responded differently depending on how much they thought the wine cost. So we could trick our brains into thinking just that it does actually taste better simply because it costs more. So this is really kind of fascinating, and you can see this in the fMRI images. These aren't the actual images from the study, but you would be able to notice clear patterns of difference across the different conditions of the independent variable. So there's all kinds of interesting studies being done with the fMRI. So concept check here. Name that imaging method. Number one, Johnny falls off his skateboard and lands on his head. At the hospital, they put him in a machine that uses a magnetic field and radio waves to produce a 3D image of his head. So we talked about four of these: CAT, the PET, MRI and the fMRI? Answer is the MRI. 2. Lacrosse player gets hit in the head with a stick. Thereafter, images are taken of her head with a machine that uses X-rays to produce 3D images. That would be the CAT scan. 3. The lacrosse player also suffered a concussion. Later, she participates in a study assessing the cognitive effects of concussion. As part of the study, she solves memory problems while in a machine that records the activity in her brain by way of radioactive markers. That would be the PET scan. And then lastly, there's only one left. By monitoring blood flow and metabolic activity of the brain, this method can create real-time images of brain activity. That would be the functional MRI. All right, so those are some of the imaging technologies. Now let's look at the brain itself. So the human brain consists of 2 cerebral hemispheres, the left and the right. So the left hemisphere, as you might have learned somewhere along the line in your science education, and the right hemisphere responsible for different things. Certainly, there's a lot of interactivity between the different hemispheres. However, there's different brain centers that are primarily responsible for different things located in the left and the right hemisphere. So left hemisphere, for example, language centers, it's responsible for most mathematical computations and so forth, logical reasoning, whereas the right hemisphere concerns more so than the left, spatial reasoning, face recognition, and music, like pitch and so forth. So there is cerebral specialization. Different parts of the brain do different things. You might have heard about people being right-brained or left-brained. And I'd just like to say that certainly scientists know that there's localization of function. There's different parts of the brain located, or there's different structures and so forth in the different parts of the brain that are primarily responsible for different things. Certainly that's the case. Whether or not somebody is using one side of their brain more so than the other, predominantly, there's no good evidence to suggest that we're sort of lopsided one way or the other. Actually, the brain is highly integrative in its action. That is, there's left brain activity and right brain activity going all the time. So whether somebody's right brain or left brain is really not the point. You look at people that are musicians and artists and that sort of thing, and you might say, oh, they're more of a right brain person because we know that there's, I guess, predominant activity when we're processing information that's auditory and that sort of thing going on in the right brain. People who are maybe the more logical and mathematical or analytical or problem-solving types, we know that that's going on in the left brain. But just because somebody has an inclination to be good or pursue these sort of things, interested in pursuing these different things, one's an artist, one's a theoretical physicist, doesn't necessarily mean that sort of they've got a kind of a lopsided brain. It doesn't work that way. The brain is really a fascinating mechanism. It's integrated. Most of the brain is being used for all kinds of different stuff, not just one side or the other in most people. All right. So the human brain, let's look at it. So let's look at the cerebral cortex. The cerebral cortex is that convoluted outer surface of the brain that most people are familiar with. The cortex can be divided into 4 lobes, so we'll look at each one of these lobes. We'll start with the temporal lobe. Again, localization of function, meaning that there's different parts of the brain, these lobes that are predominantly responsible for different things. Now, each one of these lobes is responsible for a number of things, and certainly if one part of the brain, one lobe gets damaged, another lobe can often pick up and take over for that part of the brain that suffered trauma. So we'll just go through these really quickly. So the temporal lobe, that's on the side of the brain, having to do with memory, emotion, hearing, and language. And the frontal lobe, that's in the front here, has to do with decision making, problem solving, and planning. So this is the area of the brain that Phineas Gage suffered damage from. So he was quite a different person after his injury. He became what they call a frontal lobe personality type, that is impulsive, unable to anticipate the consequences of his actions, unable to control his sort of more basic emotions like anger and euphoria and stuff like that. Uh, Parietal lobe, concerned with reception and processing of sensory information from the body. So there's a strip in the parietal lobe known as the somatosensory cortex that you can take an electrode. If you've got somebody's skull open, you can take an electrode and stimulate different parts of that parietal lobe, and they'll actually feel the sensation in the different parts of their body. And I also wanted to back up to the frontal lobe. So there's a strip in the frontal lobe that's also associated with motor behavior. So again, you can go in and stimulate the part of the frontal lobe, the motor cortex, and people will move their big toe, or they'll move their finger, or whatever part of the brain that's associated with that kind of motor behavior. And then lastly, we have the occipital lobe, that's concerned primarily with vision. That's in the back of the brain. All right, so can you name the lobe and one function? You might want to pause this for a second and maybe rehearse that a little bit before we do this concept check. All right, can you name the lobe and one function? Let's start with number one. What lobe of the brain is associated with number one in the image? That would be the frontal lobe, planning, problem solving, decision making. Number two, the parietal lobe, processing sensory information. How about number three? That would be the occipital lobe, predominantly responsible for processing visual information. And number four, it's on the side of the brain, the temporal lobe, language, hearing, memory, and emotion. All right, so know those lobes of the brain, four lobes, and their functions. So let's look into the interior of the brain. We've been looking at the cerebral cortex. That's the outer, convoluted outer surface of the cortex. So now let's look at some of the different parts of the brain: hindbrain, midbrain, and forebrain. We can parse the brain into those three different areas, and we're going to look at each one of them. So let's look at the hindbrain first. So the hindbrain is said to contain the cerebellum, which is back here. This means little brain. The medulla, which is here, and the pons, which is here. So the cerebellum you can think of as being primarily responsible for coordination of movement, balance, fine motor skills. So you suffer damage to the cerebellum, and you're going to have trouble with fine motor behavior, with walking, and so forth. The medulla, breathing, circulation, muscle tone. So you damage the medulla, and it could be that if the damage is severe enough, you have to go on a respirator because you've lost the ability to regulate those basic bodily functions. The pons, that helps us regulate sleep and arousal. So there's something in the brain that supports us falling asleep and waking up. So the pons supports that. And then there's this structure known as the reticular activating system that supports sleep and arousal too. Midbrain, a reticular formation known for its role in sleep and formation, so that runs through the pons and the medulla. So this is the part of the brain that's active when we find ourselves feeling drowsy at night, and also that gets us up usually in the morning. That's the structure I want you to know for the midbrain. And then the forebrain has a cerebrum, the thalamus, the hypothalamus, and the limbic system. So the cerebrum is that convoluted or that surface of the brain or the cerebral cortex runs over the cerebrum. So the cortex covers the cerebrum. We call that the seat of complex thought because that's where most of the higher order cognitive processing takes place. So when you're thinking and problem solving and that sort of thing, creating, that's the cerebrum at work. And then the thalamus down here is known as the way station for sensory information. So all the information that's coming in from your senses, your visual, auditory, and so forth, is being processed through the thalamus, and then it's sent out to other brain areas. The hypothalamus down here, below the thalamus, basic biological needs related to survival, feeding, fighting, fleeing, and mating. So when we're hungry and so forth, and sexual motivation and so forth, that is those basic drives are being governed by the hypothalamus. And then the limbic system is known as the seat of emotion. So this is a constellation of brain structures that include the cingulate gyrus, the fornix, the septal nuclei, the mammillary bodies, the amygdala, and the hippocampus. So these are the two I want you pay attention to because you might see them on a quiz or a test. So the amygdala is a little almond-shaped structure, very important in the experience of emotion. So it works in conjunction with the hippocampus, which is very important in creating new memories, consolidating memories. So emotion and emotional memory are very, very important because they allow us not only to, memory calls us to, enables us to recall events and so forth, and possibly use that information to plan ahead, but also there's emotions that accompany memory. So emotion and memory are intimately tied up together. So for example, when people experience trauma, that information is created, those memories are being created, those emotional memories are being created by and large by the action of the limbic system, including the amygdala and the hippocampus. So with Phineas Gage, again, we'll go back to Phineas. So that spike probably went through his brain, separating out these lower brain centers, lower meaning that they're below the level of the cortex. And separated those lower brain centers like the limbic system from the frontal lobe. So supposedly one of the explanations for his impulsive and reckless behavior and his inability to control his emotions and so forth is that the frontal lobe has some control over the expression of those more basic motivations, sexual motivation, and so forth, that are being generated by those lower brain centers. So his lower brain centers were sort of free to fire at will, if you will allow me to say that. That is, they were able to do whatever it is that they do without the regulation of the higher brain centers in the cortex. All right, so let's look at the different parts of the brain that we've just talked about in this concept check. So John has suffered damage to his blank, and now because he eats uncontrollably, he has problems with obesity. So what part of the brain that we just talked about can be used to fill in the blank? That would probably be his hypothalamus. 2, Miranda's on a respirator and cannot breathe on her own. She's probably suffered damage to her medulla. So if somebody gets in an accident and they can't breathe on their own, probably they've suffered damage to their medulla. 3, because her hand shakes so much when she draws, Susan, an artist, can no longer create the fine pencil sketches she was known for prior to her accident. Susan probably suffered damage to her cerebellum, the little brain. And then lastly, after a severe head trauma, Riley has great difficulty with planning ahead, and with judgment, he's probably suffered damage to his frontal lobe, probably more specifically the prefrontal cortex. It's a part of the frontal lobe that supports planning ahead and judgment and regulation of emotion and that sort of thing. Prefrontal cortex. All right, lastly, we want to touch on brain plasticity. So your brain is incredibly adaptable. That is, if people suffer trauma, that is, it's either external trauma, as in the case of Phineas Gage, or internal trauma, as in the case of strokes. People can often recover and lead either normal or pretty normal lives. Phineas Gage actually was able to continue to survive and live for quite a while. He wasn't the same guy, but he still was able to survive because different parts of the brain sort of picked up for the parts of the brain that were damaged. You see this in stroke. Often people are highly impaired cognitively, and motor behaviors are impaired immediately after the stroke, but then over time, people are able to recover quite a bit of what they've lost due to the stroke. So think of brain plasticity as the lifelong ability of the brain to reorganize neural pathways based on new experiences. So this is really fascinating because when you're learning and you're experiencing different things, your brain is actually changing. The physical structure of your brain is actually changing due to those experiences. So we're designed to support, um, I guess, curiosity, and imagination, and experience. We're wired to go out and actually um, explore and do these sort of things. Our brains actually change as a result of that experience. So learning not only is a acquisition of new knowledge and behavior, but it's actually changing the physical structure of our brains. New dendritic connections and that sort of thing are being formed all the time based on new experiences. So the second bullet point, during brain repair, following injury, plastic changes are geared towards maximizing function in spite of the damaged brain. So again, if somebody suffers a stroke and a part of their brain is damaged, like the language center on the left side of the brain, Broca's or Wernicke's area are damaged, then over time, different parts of the brain will begin to support the deficit. And certainly there's some parts of the brain that, when damaged, will lead to more severe deficits than others. But our brains are designed to sort of pick up, like a team member can, when another part of the team is injured. Third and last bullet point, brain cells change in their function and shape, and they take on the functions of the damaged or missing cells. So again, this is the incredible plasticity of the brain. Our brains are designed to pick up and take over when another part of the brain is damaged. All right, so I want you to, when you're done watching this, go to our supplementary websites and click on neuroplasticity and watch this very brief video, YouTube video on neuroplasticity, and it's about a little girl who lost half of her brain and was able to continue to lead a nearly a completely normal life. So I'd like you to watch that. So learning objectives, make sure you review these learning objectives. Any questions about any of these, make sure you ask me, but you can expect test and quiz questions to come from these learning objectives.